So how do you use this? Turns out to be actually very easy to use in periodic orbit theory. And the reason is that our condition, so now we'll do this special case. I'll do it for dynamical zeta function. So the way the dynamical zeta function condition, vanishing condition, looks like is that it's 1 minus sum of pi, and then the weight of pseudocycle pi. And what is a pseudocycle? Pseudocycle pi is a product of all prime cycles, some set of prime cycles, but never repeated. So this means not repeat. And this condition of no repeat of prime cycle is called Mobius inversion in number theory. It's intrinsic to definition of zeta function. But the way we derived it, it's obvious. And then each cycle in this product has its weight, and its weight average of the observable on the cycle minus s times its period divided by the product of expanding eigenvalues on the cycle. Should we just call that lambda p? This is product of expanding eigenvalues, stability eigenvalues, or Floquet multipliers, expanding Floquet. And when we take a product, everything is an exponent, so we can define observable for a pseudocycle to be the sum of all the prime orbits that happen to be in a given pseudocycle. We can define the period of pseudocycle. That's an observable is just 1, so when we integrate along, we only compute the length of the time integral, which is just the period. And now we can actually explicitly evaluate these two quantities. So this is our f. We're looking at it 0. So when you take the first derivative, what will happen is, with respect to beta, only dependence in beta is here in the exponent, and you just bring out the dual variable, which is expectation value of accumulated thing computed on a prime cycle. So df d beta, this object in the numerator, evaluate at beta equals 0. It just brings this thing down. So it's a minus sum for all pseudocycles. And each one of them just has observable accumulated over all parts of the pseudocycle. If you take derivative is variable dual to time, you just bring time down. By the way, this is plus, I'm sorry. Minus, and let's, before we said beta equal to 0, what are these objects? So when I take the beta of p, this is the sum of A for the pseudocycle times the weight of the pseudocycle. So that looks like probability. And we can make it into probability by, there is a sum rule that says the sum of these weights must add up to 1. That's called probability conservation. So what this is simply the expectation value of our integrated observable A evaluated a particular pseudo-prime cycle using zeta function as a weight. So I'll put a little zeta here, meaning we are using zeta function weights. So now what do we have? This is just expectation value of integrated observable, and this is the mean cycle time if we sum it up over all periodic orbits. So what this derivative is, the minus signs go away because of that, and it's just expectation value of our accumulated observable A divided by the mean cycle time. But that is, by definition, expectation value of A. So in periodic orbit theory, at least in zeta function formulation, the expectation value of observable is extremely easy to compute. It's simply sum over all cycles that contribute to zeta function, but weighted by observable accumulated on each pseudocycle, divided by time computed on each pseudocycle. So it's brilliant, it's very simple. Now we also have to compute the second derivative. So let's go and proceed with the second derivative, because you'll be interested in diffusion. So we have it here. And it was divided by df ds. That's the calculation. But now we can rewrite this in terms of periodic orbits.